Well, with this video, we're at day 6 for chapter 3. Things are going to switch around a little bit. Instead of talking about energy and work and power and conservation of energy, we're going to switch around to being ready for collisions, where we focus on momentum, conservation of momentum, and impulse. So the first part of this switch over is just going to be some review back to Physics 11. For Physics 11 and for Physics 12, momentum is actually just going to be the mass of an object multiplied by its velocity. And it is a vector. Whichever direction the velocity is going, that's the direction that the momentum is going. Okay, the units for momentum, all we do is just package together the units that we've already got for mass and velocity. So it's just kilogram meters per second. More important than just calculating momentums are the ideas of conservation of momentum and impulse. So impulse is what happens when you take Newton's second law, F equals ma, and say, well, the A, if you think about A, is just change in velocity divided by change in time. So that's kind of like saying this: net force is equal to mass times change in velocity all over time. And if you multiply both sides by time, you can create this equation here. And I should have put in that this needs to be the net force. But net force multiplied by time will equal mass times change in velocity. We actually give a name to the idea of force multiplied by time, and that's called impulse. And it's measured in Newton seconds. And over on that right-hand side, it's not actually momentum. It's change in momentum, right? How much the momentum is going to shift by. Now, I guess if an object starts with zero momentum initially, then whatever change you've got would be its final momentum. They'd be the same. But generally, this idea of impulse is that it tells you very quickly how much the momentum of your object would change. And the units for change in momentum, well, it would be the same as the units for momentum, kilogram meters per second. But this can be a little bit of a shortcut. If you're asked to find impulse, you can find change in momentum instead, and vice versa. Conservation of momentum. I know it kind of seems like there's a whole bunch of theory just being thrown at you on this page. Well, the neat thing is, by the time you get to the bottom of this page, that's all the theory there is for the rest of the chapter. Conservation of momentum says this: for a whole system, if you include everything, what we sometimes call a closed system, if you add up all of the momentums initially, you're going to get the exact same total when you add up all the momentums finally. An incredibly useful tool for working with collisions, where some objects are moving around at the beginning, they bump into each other, and then they're moving around in the end. They're going to do it in a way where momentum is conserved every single time. So that's the theory for the rest of the chapter. Now all we're going to do is just get really good at working with that. Let's try this first one out. Got a 45 kilogram rocket, has an initial velocity of 420 meters per second going north, and it's going to be given a push from a rocket engine. The force is going to be 600 newtons. That's going to be a push to the south. So this rocket must be kind of turned around backwards, coasting backwards through space. We're going to fire up the engines for 12 seconds, and we're going to try to find the final velocity. I can't say this too many times. You absolutely could do this one the way we did at the very beginning of the course. You could draw a free body diagram. There would only be one force on it. You could add all those forces up, well, there's only one, to come up with the net force. You could then do F net equals ma to find the acceleration, and then you could do kinematics to find the final velocity. It absolutely works. However, if you notice that there's a discussion about this net force and time, if you pick up on that, then you can say, hey, I have a shortcut. I could work with impulse. If I had force and distance, then I would say, hey, I have a shortcut. I can use work. But the shortcut for working with forces and times would be impulse. So this is optional. Instead of doing what we did in chapter 1, you could do this instead, and it's very fast. So I'm going to call anything going north positive. That's what I mean by that little arrow and the plus sign. So when I do my math, that'll be a positive 420, but this will be a negative 600 because it's off to the south. And here goes. In one line, I can get this done as long as I respect the fact that changes in velocity are finals minus initials. So I would have this. One line, no need to find the acceleration first and then do kinematics. I have my backwards force, time of 12, mass, changes in velocity when I go final minus initial. And the final velocity is still positive, so it's still going north, but not as fast. So this is an optional way to quickly get to the answer if you notice that there is talk about force and time. Okay, it's just a quicker way than what we did in chapter 1. Let's try one that's actually significantly more challenging. This one's going to be two-dimensional. A 12-kilogram shopping cart is going 2.4 meters per second north, and unfortunately it bounces off someone's car, and afterwards it's going 1.8 meters per second, but at some awkward angle, 60 degrees south of west. And they're asking for how big, right, that's all that means, right, the magnitude. How big is the impulse given to the cart by that bumper of the car? So think of impulse as being like a shove, right? They're asking you for that product of force and time. They want the left-hand side of this equation. They're asking you for that. There's no way that we can directly calculate that because we don't know the contact force or the contact time from the bumper. So at first glance, I'm looking at this story going, how do you expect me to find this impulse? But I can cheat. I can go and find the change in momentum instead. So if I take the mass of the cart, got it right here, and multiply it by the change in velocity, I'm there. But just be super careful. It's all two-dimensional. So the calculation of that delta V is the significant part of this question. As vectors go, we have to respect that you're taking this final velocity vector and subtracting the initial velocity vector. And we're going to accomplish that subtraction by doing an adding of the opposite. That bracketed part is what's going to take us the most time with this example. Just finding the VF, 1860 south of west, plus the negative of VI, the opposite of 2.4 north. Okay, here goes. There's my 1.8. There's my final. That's me doing this. And now I'm going to add on the opposite of 2.4 north. Well, the opposite of 2.4 north would be 2.4 south. So all of this work that I'm doing right now, I'm just trying to find how big that bracketed part in this story is. Looks like I could probably do the cosine law here, maybe little Z-shaped angles will get me going here. I've got a 60 degrees and then 90 more. Yeah, that's 150 degrees. So yeah, there's a little bit of geometry in there, right? Like 60 here and then 90. So 150 degrees. And now we can deploy the cosine law and find out how big that delta V is. You could even find the angle if you really wanted to. This question just says, no, how big is it? So, okay, we won't worry about the angle. So finding out the size of that subtraction of the velocities involves the cosine law. It's a side angle side situation. So I take the square root and I find that the change in velocity is 4.06. And there's no way you can get that number simply by taking 1.8 and subtracting 2.4, right? You end up with like negative 0.6, right? Not even close. So we have to respect the fact that this is a nice Physics 12 two-dimensional question. Well, we're almost done. That's the delta V. We're still cheating, trying to find out the impulse. We're trying to find this, and right now we have that, delta V. If we just multiply by the m, we have it. It looks like the change in momentum is around 49 kilogram meters per second, or 49 Newton seconds of shove, right? So those units are interchangeable, Newton seconds for impulse and kilogram meters per second for change in momentum. Okay, let's try a couple of collision questions out here. I've got a 4.8 kilogram lab cart, and it's going east pretty fast, and it's going to collide with a smaller lab cart going 1.5 west the other way. And they're asking me to find how much heat and sound there is. Oops, didn't mean to cross that out. Fix that. They're asking me to find out in this story how much heat and sound energy is involved. Don't go there first. Whenever you see that there's a collision, every single time, momentum is your friend. Use momentum to help you find perhaps a velocity, and then later on we'll look at this heat and sound thing. But you can't go there right away. So you've got to pick up on that word collision or collides and say, yeah, I'm going to go with the idea of conservation of momentum. The idea that the total momentum before, when the lab carts are moving independently, is equal to the total momentum later on. Okay, that gets me rolling with this. Here's the momentum for the first lab cart. all I'm doing is m times v. That's it. And here's the momentum for the second lab cart, m times v. They were both 1.5s. Now this one is going backwards. Momentum is a nice, helpful tool to work with collisions, but it's picky. It wants to know if things are going the wrong way, so I have to put that minus in. And the 6 is what happens when the 4.5 and 1.5 kilograms stick together. They form this 6 kilogram blob. Super nice. The total momentum is a 12 and a negative 2 is 10. And when we divide by the total mass, after they collide, those lab carts have to be moving this fast. There's no way around that. And so conservation of momentum helped me with that, and I knew I was going to use conservation of momentum as soon as I saw it was a collision. Now, here's the thing. We're going to find in this story that there's not enough energy left, right? The velocity's right to conserve momentum, but there's actually a loss in overall kinetic energy, and that's been converted to some heat and some sound. So I'm going to try to just keep track of my energy here. And what I've got is some kinetic energy from one cart and some kinetic energy from the other cart. There's a lot of kinetic energy there, right? Almost, what do we have? Almost 19-ish or so joules. And then afterwards, there's only about 8 left in that combined cart. And so we've lost some, and it's been converted to heat and sound. It's not an accident, I have deliberately left off the minus sign on this velocity here, even though I put it in on the top calculation. Momentum cares, and you have to put in backwards velocities as negatives. Kinetic energy does not care which way things are going. It just wants to know speed. So it's actually good form to not put it in on that lower calculation. And so when we're done, we've got the answer. It looks like 10 joules of that kinetic energy from those carts is lost and must be now in some form of heat and sound, some combination of heat and sound. If you want to look at this from the point of view of conservation of energy from a couple of lessons ago, it would actually look like this, right? There's the big equation. But now we've got no hills, so the potential energies are gone. There's no ELF. And instead of a single kinetic energy at the beginning, there were actually 2 lab carts moving at the beginning. So that story would turn into this. You've got one initial kinetic energy, another initial kinetic energy, one final kinetic energy, no potentials, no work from any ELFs, and then there is some heat and sound of 10 joules. Okay, let's try another one out. This one's going to be kind of like that last one where objects stick together but in reverse. This is an explosion. And explosions are just collisions backwards. So we've got a 68 kilogram skateboarder on a 2 kilogram board, and they've also got a 10 kilogram backpack on them, and they're going forward at 3.4 meters per second. And maybe they desire to go faster, and they don't really care about their homework, so they actually take their backpack and kind of like a rocket engine, they throw it backwards at 5, and we're going to try to find the speed of them and their board as they roll away from the story. So it really is just a collision of them and their backpack in reverse, right, as they explode and their backpack goes the other way. So if it's just a collision backwards, I'm going to go with the same math. I'm going to go with conservation of momentum. So I've got at the beginning one big giant mass, 80 kilograms of skateboarder, boards, and backpacks, all going forward, there's my positive, at 3.4. Afterwards, the 70 kilogram kid and board is moving with one speed. There's the momentum for that. I'm just adding up all the momentums. And here's the momentum for the backpack going backwards at 5. So if it is going backwards, I have to let momentum know about that. Super nice. It all falls apart pretty quickly here. That negative 50 goes over to the other side, makes it even bigger. We divide by the 70, and we can find the final velocity. So this kid has actually managed to increase their speed from 3.4 up to 4.6. It's kind of a one-time deal, though, right, as you throw your backpack away. But they have managed to make themselves go faster. An interesting little follow-up question to this is how much energy did that add to the whole system? There is actually an energy gain here, which should make you wonder, like, well, where does that come from? But there is an energy gain, which we can go and figure out. So if you check out the kinetic energy before the collision, we had just the whole big 80 kilogram mess of a kid and their backpack and the backpack going at 3.4. There's 462 joules of energy at the beginning. Afterwards, there are 2 energies that I have to add together. There's the 70 kilogram kid and board going at 4.6. And then there's the backpack going backwards at 5. Notice I did not put the negative in on the 5 because it's just good form not to. Energy doesn't care. And this 4.6 number, there's no way I could have found that number without trusting the momentum calculation at the beginning. So that helped me get this 4.6. And now I can see that we've gone from 460 joules up to 865. So there's definitely been an energy gain here. And if you were to just subtract, you can see that the energy gain is a little bit more than 400 joules. Now, two last thoughts on this question. If you wanted to, you could ask, well, how does that look in terms of conservation of energy? You know, where does that all fit in? We've actually had some work come into this problem, right? We had a little bit of kinetic energy, 400 joules at the beginning, had some work of 403, and now we've got a lot of kinetic energy afterwards. And so this would actually turn into that. And so final thing with this question, where does this work in come from? Where's the elf? And it turns out it's the kid with their arms. When they throw that backpack backwards, they're doing some work, and they're going to be tired. They're going to have to go home and have lunch, right? Because they're going to have used some of their breakfast energy. Well, they're going to have to explain to mom or dad where their backpack is too, but they're going to have to go home and have lunch because they've done some work, and that's going to make them tired. Last one. This one is about a rocket engine, and we're going to try to find the force that the rocket actually gets pushed with. And it's kind of like the kid in the backpack. The backpack would be the gas all being shoved out of the bottom of the engine. And as we shove the gas out the back of the engine, that shoving backwards with Newton's third law is going to push the rocket forward. And so this story here says we're going to be shoving gas out the back of the rocket continuously at 480 kilograms per second. So that's just happening second after second after second after second, as long as we have fuel in the rocket. And we're going to be shoving it out the back with an incredible velocity, okay, of 2,500 meters per second. And we're going to try to figure out how much force we can create on the rocket with that. We're actually going to do it in kind of a sneaky way. It's actually easier to figure out how much force we have to shove the gas with. But Newton's third law says by doing that we'll have found the answer. But let's just consider the gases as we shove them out the back. This is the first time that we've actually in Physics 12 played with this mass flow rate, this kilograms per second. I mean, I understand kilograms, but what's with this kilograms per second? And it turns out this is just happening every second in a continuous basis. But don't worry about that. Turns out we'll actually find a great spot to insert that if we just take this story about the impulse, the shove on the gas out the back, and just solve for force. Right? We're trying to figure out how much force do we have to continuously apply on the gas as we keep shoving it out the back. And if we divide by time, we're going to end up with force all by itself, we're trying to solve for that, is equal to the change in momentum for the gas as it's continually shoved out the back, divided by the time. Now, at first glance, I'm really troubled by this whole continuous thing, right? How does it happen continuously? But take a look. You've actually got an m divided by a t. So m divided by t, there's your mass flow rate. You know, basically, it's kind of like you're saying, well, if I go for 1 second, it's 480 kilograms. But a more elegant way is to say, no, it's m over t. It's a mass flow rate. That's where the 480 goes. And then here's the 2,500. So it finishes off with a really simple calculation. You just take the two numbers and you multiply them together. 1.2 million newtons of force, right, as we're shoving that gas out the back of the rocket. Right? So quite a bit of force involved there, right, to launch this rocket up into the air. And that's where we're going to finish today. And then next day we're going to take a look more closely at working with one-dimensional collisions.